Hi, everyone. I think we can start our session. Thank you for joining this lunchtime event. It's my pleasure to welcome you all on our talk on probabilistic analysis for the seismic resilience for transportation networks. And before we get started on the talk, let me list a few housekeeping rules. Please, can everyone keep their videos off and microphones on mute during the presentation? We will have a Q&A at the end of the session, so please type your questions in the chat, or if you wish, you can raise your hands and come off the mute and ask your questions. When you attend this event, please note that your name and email address will be recorded on a list of participants. The list will be used for improving our services in the future. We will not pass on your details to any third party, and we will not send you any unsolicited emails. If you don't want to be included on the list of participants for this event, please contact us on the email address given in the chat. And please note that the seminar will be recorded and uploaded onto our YouTube channel. By dialing into the event, you consent to any information or views you share during the seminar being made public. As the chair for this event, it gives me great pleasure to welcome Dr. Ji-Eun Byun for this lunchtime presentation. Dr. Ji-Eun is a postdoctoral researcher at Engineering Risk Analysis Group, Technical University of Munich, Germany. Her specialism lies in reliability analysis and reliability-based optimization of structural and infrastructure systems against extreme events, including natural and man-made hazards and structural deteriorations. She's particularly interested in analyzing complex and large-scale systems such as transportation networks, utility distribution systems, and structural systems, for which she has developed novel reliability methods that can handle high-dimensional probability distributions. Her research also includes an interdisciplinary management of infrastructure systems, for which she has been employing probabilistic graphical models to integrate data and methods from various disciplines, such as engineering, social science, and finance. Through these efforts, she ultimately aims to enhance our community's risk intelligence so that we can effectively design and manage our engineering systems. Without further delay, I will hand over to Ji-Eun. Ji-Eun, please.
Then I will share my screen. So, hello, I'm Ji-Eun, and this is my great pleasure to talk about my research at SECAD, at SECAD Young Members Seminar Series. So I am, as Asana kindly introduced, I'm currently at the Technical University of Munich. But today, I'd like to talk about my previous project that I mainly carried on in the UK at University College London, which was about the probabilistic analysis of the seismic resilience of urban transportation networks. But before going into today's presentation, I'd like to briefly illustrate what I'm currently doing at Technical University of Munich. So my research background is system reliability analysis and structural reliability analysis, as well as reliability-based optimization. And among them, I'm particularly interested in addressing a large-scale systems, in other words, those systems that consist of a large number of components, because computational cost in general exponentially increases with the number of components. So, so at the current project at TUM, we are aiming for. We are trying to develop methods for life cycle management of lifeline networks. So such lifeline networks include transportation networks, power networks, and utility distribution networks. And we are trying to come up with methods that can deal with large-scale systems of those, such as road networks with many roadways, or power networks with many transmission lines, or utility distribution networks with many pipelines. And so to this end, we need to make decisions sequentially for over large-scale systems, for which we need dynamic probabilistic models and reliability-based and sequential optimization. And so in order to apply these advanced system reliability methods for large-scale systems, we are now particularly interested in combining machine learning techniques that can rapidly assess the performance of complex and large-scale systems, and combine these machine learning techniques with advanced probabilistic models so that we can balance between accuracy and efficiency of reliability analysis. So this is where I am at the moment, but today's presentation is about my previous project, which is almost coming to a conclusion right now. So this project was carried out under a larger research hub named Tomorrow Cities. So Tomorrow Cities is a global interdisciplinary research hub that has been funded by UKRI. And this research project aims to reduce the disaster risk for the urban poor in low to middle income countries. And technically, our objectives is to achieve interdisciplinary research, combining risk assessment with urban planning and policy, and engaging diverse stakeholder groups. So the research hub consists of universities based in the UK and 4 focus cities, which are Istanbul, Quito, Nairobi, and Kathmandu, that have been selected to represent such low to middle income countries. And we are also constituted by researchers from backgrounds of both physical and social science so that we can successfully carry on interdisciplinary research. And under this theme, our working package's objective was to evaluate the seismic resilience of urban transportation networks. In other words, in civil engineering, we have hazard models and structural models to measure the structural damage of our structures. But on the other hand, we need to combine these models with additional data sets such as repair and recovery data sets and other theories such as graph theory, so that we have to predict and make effective decisions against system-level consequences. And we have another, and in this project, we have another question, which was how we can connect this engineering analysis result to practical decision-making. And so this presentation is how we resolved these issues through this project. And before going into the methodology, I'd like to briefly illustrate the city Istanbul, which is the capital city of Turkey. And this city will be the case study area throughout this presentation. So Istanbul is such a mega city, having population more than 15 million, and it identifies its major hazard risk as earthquakes. So you can see that not only the population, but also the spatial scale is huge for this city. And as typical of a mega city, the central areas are characterized by very dense development, which means that these about which we were concerned of the secondary traffic disruptions caused by the debris generated from adjacent buildings and overpasses. In other words, even if the roadway itself does not experience any structural damage, the traffic might be disrupted because of this debris blocking the roadways. On the other hand, in non-central areas, they are characterized by insufficient provision of infrastructures. And this may lead to road network topologies that are not very robust to minor disruptions. So in other words, even a slight disruption at a part of even some local disruptions may easily propagate to the other part of the networks because of the lack of redundancy in the network topology. And one of our original attentions was strengthening the capacity of the urban poor because in reducing the disaster risk for the urban poor was the central objective of the whole research hub. So to this end, we wanted to investigate the disaster inequality issue around the city. So to resolve this issue, we produced seismic resilience maps of Istanbul's transportation networks. So this was the background and motivations behind the research that will be presented today. And today's presentation is twofold. First, we started with analyzing the seismic resilience of the transportation network using Bayesian network. So for which I will first illustrate what Bayesian network is, and then illustrate our proposed models and employee data, and then I will present the analysis results and their implications for practical decision making. And then our next question was if we can make this analysis more affordable and accessible so that we can expand this analysis to the city level. So to this end, we developed a resilience analysis toolkit so that stakeholders can use the toolkit to examine various decision scenarios and scenarios. And then I will illustrate, and after illustrating the toolkit, I will present the analysis results and their implications in practice. So the analysis results are still preliminary because we are now trying to adjust the model parameters and settings to capture the reality more accurately. But I still brought them today because they are insightful at this stage as well. And then I will conclude this presentation with the concluding remarks. So then let's begin with Bayesian network. So Bayesian network is a probabilistic graphical model, which means that it visualizes probability distributions for its formulation. So in a Bayesian network, each node represents a random variable, and the directed edge between a node pair represents a directional dependence between this node pair. So for example, in this Bayesian network, we have two random variables, and they are connected, and they can be connected to represent their statistical dependence. Then once given a Bayesian network graph, then we can quantify the probability distribution by assigning a conditional distribution to each node being conditioned on each parent node. So for example, in this Bayesian network, X has no parent node, so it is quantified by your marginal distribution, while Y has a parent node as X, so it is quantified by a distribution that is conditioned on its parent node. And then the joint distribution that is represented by this Bayesian network is simply the multiplication of all these assigned distributions. And this idea of Bayesian network is powerful for system reliability analysis because, first of all, it facilitates modeling such a complicated dependence between multiple variables by using the causal relationship between random variables. And this is useful because such causal relationship is quite obvious between real-world variables. And also by by representing the statistical dependence in such a hierarchical way, we can easily integrate models and data sets that are defined for different variables. So based on this idea, we propose our Bayesian network as follows. So in this Bayesian network, we have these nodes that represent hazard processes, specifically ground motion and permanent ground displacement. And we introduce these nodes that represent the structural damage of paved roads, bridges, and adjacent buildings. And we have this recovery process of structural repair and debris clearance. And then finally, we can compute the traffic capacity of the roadways for each roadway at each time point. And then we can evaluate the system's functionality, which we defined as a maximum flow from each node to the highway junctions. And finally, by assembling the system functionality at each time point, we can evaluate the resilience metric. So this list shows employee data sets and models we use to quantify the distributions of these components in the Bayesian network. And I'd like to underline that there are quite a few data sets for which either local data sets are absent or remain highly uncertain because of lack of preceding studies and literatures. And this highlights the need for the further efforts to fill this data gap so that we can make our analysis more accurate. And for this resilience metric, we used this conventional definition of resilience, which measures the loss of the functionality from the beginning of the damage to the full recovery. And so in this resilience triangle, the y-axis is usually defined as time, while the y-axis represents the system's functionality. And then here, we define this y-axis as the maximum flow to destinations for each location. And then we computed this maximum flow and we define this y-axis as a ratio between the reduced maximum flow compared to the original maximum flow. So that's why this y-axis is represented as the ratios. And we apply this method to our case study area, which is the areas around the Fikirtepe neighborhood in Istanbul, with this around 6 by 4 kilometers of spatial scale. And in this area, we have 10,000 roads and 7,000 intersections. And as a result, we could obtain this resilience loss map, from which we can investigate the magnitudes and the spatial variations in the resilience loss. So in this map, the brighter the color is, the higher the resilience loss is. And we found two principal factors that determine the system's resilience, which are network topology and building density. So, and in particular, these disruptions by debris are not often considered in resilience analysis, but we found that they can lead up to 15% of difference in the analysis result. However, on the other hand, it should be caution is needed because there is a great uncertainty in debris modeling, for which we could not find much preceding studies to refer to. And also, we found a different impact of the repair works, and we found that the instant disruptions were governed by the debris clearance work, while the long-term disruptions were observed by severely damaged bridges. And to understand a little more, to understand the results better, let us take a look at example locations. So we found that when an area is given with a high building density, which is represented by this brighter color in this purple map, and if such high building density is combined with an inefficient topology of the networks with many dead ends of the roadways, as we can see in this map, then we can see this high resilience loss. In other words, low resilience. On the other hand, we found that such high building density can be compensated by efficient topology because in this area, the roads are very well connected, and therefore we are observing only a mild resilience loss. However, the situations are not that obvious in all times, because in these two areas, the areas both have low building density and with inefficient topology with many dead ends, but this area shows mild resilience loss while this area shows high resilience loss. And this underlines the importance of system level analysis because these individual factors are not fully explanatory for the system level consequences. So this was the first phase of our analysis. And our next question was, then can we make this analysis more affordable and accessible? And to answer this question, we developed a transportation resilience analysis toolkit so that the analysis can be more accessible for local stakeholders. So first, we wanted to make the computation more affordable so that we can expand the analysis to the system level. To this end, we evaluate the resilience at each district level instead of each location across the map. And we replace the evaluation of the resilience metric from maximum flow analysis to connectivity analysis. So now we are defining this y-axis as global efficiency or the connectivity to critical destinations, which can be evaluated by connectivity analysis. And we are now considering only highways, but still we are considering both disruption modes that are incurred by roadways, structural damage, and building debris. And also, by utilizing such a toolkit, we can make the analysis procedure more accessible because now stakeholders can access to the employed data and methods and validate them. And also, we can put different data sets and functions to examine problem-specific settings. And so this is how the toolkit looks like. So it is MATLAB-based, and it accepts different data sets such as this information on district, roads, intersections, and the fragility curves and the recovery models. And we also incorporated the multiple analysis modules, so that which can be used as each step of the analysis procedure. And this list again shows the employee data sets and models that we used. And the list is generally similar to the previous one, but varies to some extent to adapt to this new setting of the analysis. And this is the preliminary analysis results that we obtained so far. So we evaluated the resilience loss matrix for 974 districts in Istanbul. So in these maps, the redder the color is, the higher the resilience loss is. And we obtained these maps by defining the system functionality, in other words, this y-axis, as global efficiency of network topology, as well as the connectivity to critical destinations that include airports, hospitals, and motorway junctions. And we found that these maps overall agree with each other, but there are slight variations that primarily arise from the locations of these destination nodes. And if we look into the results in more detail, then we can compare the central areas and the outskirts area. And we can see that, and in these two maps, these circles represent the density of the damaged buildings, which in general are proportional to the total number of buildings. So, and therefore, by the sizes of these circles, we can see that at the centers they are having this high provision of infrastructures, while where infrastructures are not very well provided in this outskirts area. And as a result, we are observing higher resilience loss in general in central areas, but still we can see that there are spatial variations from district to district. And we also wanted to see how this system level resilience is connected to these individual factors. So we compare this with the level of infrastructure provision, which can be represented by this density of damaged buildings or the density of the roadways. And we can see that there are generally negative correlations between this resilience loss and the level of the provision of these infrastructures. But still, as we can see here, these individual factors are not fully explanatory of these system level consequences, because I'm sorry, because this system level consequence is determined by the interplay between many components, such as structural strengths, the infrastructure provision, and the topological robustness of their roadway networks. And using such a toolkit, we can also examine this. We can also examine hypothetical decision scenarios. I'm sorry, hypothetical decision scenarios to simulate the effect of policy implementation. So, for example, what if we implement retrofit projects that can achieve 10% of reduction in the number of damaged buildings, or 10% of the increase in the roadway's fragility means? Then we can quantify the expected reduction in the resilience loss, where in these two maps, the bluer the color is, the higher the reduction is you can expect. And if we see these two areas, then we can see that in these central areas, which are provided with many buildings and many roadways, we can expect more reduction from retrofitting the buildings. But on the other hand, in this outskirts area where there is a low provision of buildings and roadways, we can expect more benefits by retrofitting the roadways. And we can also use this result to classify districts to implement different policies. For example, if we want to decide whether to retrofit buildings or roadways, we can separate the district in this way to sort out in which district we should employ which policy. And we can think about more detailed classification. So if maybe we want to separate out this district where we cannot expect much difference in the two policies, then we can we end up with this classification. So in summary, in this presentation, I illustrate the seismic resilience analysis of transportation networks and how they can be informative for practical decision making. So our questions to begin with were how we can predict and make effective decisions against system level consequences, and to answer these questions, we built our Bayesian network-based model, and thereby we could integrate different models and data sets that were defined over multiple variables. And we also considered the secondary disruptions by debris, which were found to have significant impact on the resilience loss. But still, further studies are required to accurately model the debris generation process, because currently there is a great uncertainty in the modeling of this failure mechanism. And by representing the analysis results as a map, we could investigate not only the magnitudes of the resilience loss, but also their very spatial variations, so that we can investigate the issue of disaster inequality, which we found that definitely exists. And also, we analyzed two different scales of analysis, which were neighborhood scale with fine resolutions, and the entire city with district level resolution. And we also showed how the resilience analysis results can remain informative for practical decision making. And to enhance this feature, we developed our resilience analysis toolkit. And so now we are at the stage of validating the models, and to this end, we are in close collaboration and dialogues with local stakeholders in Istanbul. And through this engagement of actual stakeholders, we found the potential of the synergy effect through the collaboration between academia and practice. And this is a longer-term prospect, but in the end, I view that such a toolkit should be developed as a user interface software, so that we can, so that stakeholders who are not expert in reliability analysis can actually implement this analysis, and thereby investigate their various decision scenarios and various settings to draw an effective decision-making based on engineering analysis results. And also, as we've seen earlier, there's a lot of holes in the data sets that are currently available, for which we need to plan a structured way of collecting data and developing our models. And we are also trying to now integrate the physical and social science because in the end, infrastructure management is inherently an interdisciplinary task. And thank you for listening.
Thank you, Ji-Eun. That was very interesting and informative talk. I already see some hands up, and the floor is now open for questions. And if you feel free, please feel free to raise your hand and just come off mute and ask your questions, or else you can put them in the chat. I will read out. Okay, shall we start with a question in the chat box? So this is from Tina. how were the districts split in Istanbul? Are these local municipalities?
Yeah, so they the boundaries follow the Istanbul municipalities administrative boundaries, and actually these boundaries are the criteria that the Istanbul municipalities are gathering all other kinds of data accordingly. So the reason that we follow the boundaries is to to remain comparable with their other data sets, so that they can make decisions in coordination with other information. So it is really interesting because they have, for example, this whole set of data regarding social science, which are risk awareness for each district, or for each of these almost 1,000 districts, and education level, property ownership. So they have all these kinds of data. So I think by building this data set in engineering side, we can draw effective decisions by combining this information, and the research is currently underway.
Thank you, Ji-Eun. I don't see any other questions. Can I ask a question about the design of the network that you presented in the first phase of your research? So just to get an idea, what's the size or scale of the network, like in terms of number of nodes? Are they discrete or continuous nodes? And how is the process of assigning prior distributions to your root nodes, for example? Like, do you have enough data, or is it based on expert judgments? Or also, if you can explain a little bit more on the algorithms that you would use for the inference.
Yeah, so for the inference, we are just utilizing Monte Carlo simulation, because it is not very critical in this problem, because we are already assuming that the earthquake happened. Then it is not so a rare event anymore, because you are conditioning on this rare event. So even the Monte Carlo simulation works in this way. So we utilize 1,000 samples. And for this data set, first of all, for the scale of the road networks, for the first analysis, there are over 10,000 roadways, which are the components that can fail. And in the case of a latter case, because we are considering only highways, I don't remember exactly, but it is around 30,000 roadways. So there are like 30,000 edges that can fail in the network. Yeah, and then actually Bayesian network is a little different from Bayesian theory. So it is similar that we compute the node, and somehow we end up with some marginal distribution, which can be viewed as a posterior distribution that represents the aggregation of the whole data set. But what we do is we assign the distribution for each node, and then we multiply them. So if we say that is a prior distribution that we initially assigned to the nodes, then we computed these distributions using these data sets and models. So for example, we have this PGD model that was obtained from HEDS-MA's earthquake model. And this model is defined in terms of this ground motion intensity. So we have then this connection, and we can quantify distribution by using the model. And then we subsequently compute all the distributions that were assigned to this to get the distribution of this resilience loss node. So for example, like these damaged nodes are quantified by fragility curves in this way. Yeah. so that's why they are connected to this ground process nodes that are related to ground processes.
Okay, thank you so much. We have some more questions in the chat. First one is from Valentina. The question is, are you planning to get to loss damage assessment once the damage resilience aspects gets fully covered?
Are you planning to get to
loss damage assessment? Maybe Valentina, if you wish to come and clarify the question.
Hi, Ji-Eun. First of all, thanks a lot for your very interesting presentation, as usual. Yeah, my question, I guess, is related to, like, once you have developed this toolkit, which computes the damage resilience of buildings, and infrastructure networks, right? Are you also planning to extend it also to compute losses, so to quantify the losses after the damage?
You mean economic losses or like social
exactly.
losses?
Economic losses.
Yeah, absolutely. So there are many aspects in this like community level resilience analysis, which are like the social issue, like and economic issue and this casualty issue, and they are all in our so they are our next step. So we want to combine this analysis result with social science as well as finance to see how this is actually related to the quantities that we can actually understand. So yes, but it is definitely our very next step.
Okay, perfect. I guess that there are a lot of things in the pipeline.
Yeah,
exactly. That's the next step. Yeah. Well, looking forward to that then. Thanks a lot.
Thank you.
Okay, we have a few more questions. One question, both are related. The first question is from Tina, again about applicability of this kind of study for other hazards like floods, or have you seen relevant studies where this method is extended to other hazards?
Yeah, I mean, this method is quite new and ours, so but there are certainly many research that has been done and is going on for this kind of community level loss analysis. And yes, this study can be easily extended for other hazards, but only the problem is the existence of the fragility curves. So if we have the fragility curves for the flood for each roadway, then we can definitely extend this model. But during our research, we wanted to actually perform multi-hazard analysis, but the reason that we couldn't was because of this lack of fragility curves, because we need to understand what happens to a roadway that has been first damaged by, for example, earthquakes, or bridges that was first damaged by earthquakes and a flood immediately follows. Then how does the bridge react to this consecutive hazard events? But to this end, we need these fragility curves that are defined in 2 dimensions. But these kind of works are not yet sufficiently provided.
Thank you, Ji-Eun. I totally understand. I think at building level, this combined fragility analysis that's been developed, like using numerical methods, again, this is very less researched area, and to have analytical fragility curves would be the challenge for this kind of a model. Another question is, sorry, please go on.
It's just that another interesting topic is aftershocks. because usually earthquakes are followed by, main shocks are followed by many small aftershocks. So like examining the combined effect of these two consecutive events would be also very critical.
Yes.
Yeah.
A similar question is, can this principle of seismic risk analysis be applied to railways and highways, also buildings and structures? This
yes,
is from this is from Nick.
Yeah, thank you for the question. And yes, it is also kind of similar, connected to this my previous answer, that we can extend this to other types of networks. So as long as the networks are defined by edges and nodes, and they can be represented as a graph, then we can apply the same method. But if it is railways, then we need the fragility curves for these railways. And if it is a utility pipe, like utility distribution networks, then we need the fragility curves for pipelines. So I think the critical part is usually the availability of the fragility curves, and of course the repair models. So for example, for these highway roads, the repair models, we are using repair data from Hedges earthquake model, because they provide us the expected number of recovery days that they gathered from the U.S. Statistics until now. But we need that kind of data. For example, if it is a railway, then we need to be able to estimate how long it will take for us to repair a railway, given each of the damage states. So, yeah.
Okay.
Thank you for that.
Thank you.
Thank you.
Thank you for the question. I don't see other questions in the chat. Can I ask one more question?
Sure.
The structure of the graph that you're showing, is it based on the conditional dependencies between the variables? Are you doing any structure learning from the available data, or are you assigning the dependencies based on a judgment of what causes what?
Yes, you're right. So it's a good question, and there are two ways of constructing Bayesian network, which are based on these causal relationships, or like engineering judgments in their statistical dependence, or we can learn it from data. But the problem is that we are dealing with hazard events, which are extreme hazard events, which are really rare. So it is not easy to get enough data to run this run their relationship purely from data. So, but the good thing is that Bayesian network deals with this directional dependence. But one of the examples of such directional dependence is a causal relationship. And causal relationship is quite straightforward in case of real world variables. So that's why we construct this Bayesian network using engineering judgment. But now we are trying to understand the relationship between this physical vulnerability and social vulnerability by using these data sets that IMM, the Istanbul municipality, has for these 1,000 districts. And for that, we are going to use this structural learning from data, because we think there is enough data, which are 1,000 pairs. And then we will apply the structural learning techniques to see how they are related to each other.
Thank you. We still have about 9 more minutes if anybody has more questions to ask. I don't see any more questions in the chat. Okay, I think there is one more question. Vaga is asking, I'm working on developing a Bayesian network-based model to find impact of construction accident on project performance and having difficulties with application of Byun. Can Dr. Byun help me on this? If yes, please connect me. So she's left you the Gmail address. Do you have any comments for her?
Yeah, I'm not sure what kind of problem you have, but yeah, definitely I'm happy to talk, and yeah, I will email you.
Yeah, so maybe Vaga, if you wish to clarify some specifics of the question, or else you could get in touch later in person.
Yeah, I think I will get in touch with her in person because it is not relevant here.
Okay,
so
great.
It's based on the Bayesian network. So thanks for accepting my request.
No problem. Yeah.
So if there are no more questions, that's the end of our Q&A, and it's my great pleasure to thank Dr. Ji-Eun for this insightful presentation, and I'm sure you all enjoyed. And just before we close, I wanted to let you know that our CKID YouTube channel has been launched, and you can find the recordings of our previous events on the channel. If you just type CKID in the search bar, you will be able to find it. And today's recording also would be available in a few days. Thank you again for joining here today, and of course, Ji-Eun, for sharing part of your work with us. And also please stay tuned to CKID website for the announcement of next sessions. In the meantime, wish you all a happy holiday season. See you.
See you. Thank you for today.
Thank you for the great presentation.
Thank you.
Thank you very much. Bye.
Bye.